Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Battery Tech webinar, EV Thermal Management Fluids, Driving Performance and Safety, sponsored by PFX and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few housekeeping announcements before we begin. First of all, this webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about our speaker, download resources, share this webinar, and most importantly, participate in the Q&A that occurs at the end of the presentation. The slides will advance automatically throughout the event, and toward the end of our webinar, we'll ask you to complete our survey. Please take just a minute to complete this survey, as it helps us make these events better for you in the future. And lastly, if you're experiencing any technical problems, just click on the help icon found at the bottom of your screen, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. Now, on to the presentation, EV Thermal Management Fluids, Driving Performance and Safety. Discussing today's topic is Tom Corrigan, Director, Electrification Technology at Prestone, a PFX company. To learn more about Tom, please visit the speaker's widget. Tom, thanks for joining us. Over to you.
Michael, thank you very much for that introduction. Welcome to everybody in attendance today. My name is Tom Corrigan, and I will be your host for today's webinar on electric vehicle fluid safety. So before we jump into the content slides for today, I want to quickly just make a quick note that we're really at a critical point in the electric vehicle market, right? Over the past 10 years, we've seen technology advancements in EVs that have led to reduced electric vehicle prices, to increased driving ranges, to reduce charging times, and we're starting to get towards optimizing battery cell chemistries, right? So this is evident by, if we look at 2024 sales data, 20% of global new vehicle sales in 2024 included electrified drivetrains. Now that includes both full electrics as well as hybrid vehicles, but it speaks to the traction that electric vehicles are gaining in the marketplace. Along with this, we see regulatory agencies starting to take note and implementing new standards and specifications to ensure safe operation of both light-duty, heavy-duty, and off-road electrified vehicles. Today's webinar is very timely because one of these upcoming specifications relates directly to electric vehicle thermal management fluids. So China, the nation that's really driving and leading the way in electric vehicle technology, is implementing a new standard that we will talk about in detail today. It goes by the name of GB 29743.2. This standard goes into effect in just under 2 weeks, on October 1st of 2025, and it will demand certain criteria for electric vehicle thermal management fluids that are sold in the country of China. So it's coming. We are seeing more regulation, and this allows us to, optimize and develop the right products for this emerging market. So we're going to talk about what that development process looks like and how we can ensure that we have a safe product for thermal management in an electric vehicle. But before we jump into that, quickly a word from our sponsor, right? So you might already have a question. What is the PFX Group, right? So PFX was, as we saw in the introduction, quite simply, PFX is Performance Fluid Experts. So you can read what our marketing team put together up on this slide. But in my opinion, I like to think of PFX as the people or the experts that are behind the iconic brands that you see on this slide. If you joined this webinar, you're likely familiar with Prestone on the far left over here. It's an iconic brand for automotive heat transfer fluids or coolants. Been in the industry for nearly 100 years, supplying solutions to maintain thermal profiles within internal combustion engines. But as a company, we're much more than just automotive coolants. We have a line of appearance and car care chemicals under the Adams Polishes brands. We do stationary heat transfer fluids, household chemicals and cleaners, industrial solvents. So we go much, much beyond just automotive coolants. That said, over 50% of our business is currently heat transfer fluids or coolants. And we support both, or 3 different areas of retail or of sales. So everywhere across retail to aftermarket to OEM business. So especially in the automotive side, oftentimes the same fluid that's factory filled in your vehicle at the plant is the same fluid that you're purchasing in a Prestone bottle on the shelf at a store. So that's one of the unique advantages that Prestone has as an organization. So we're heavily North American focused chemistry, but we are growing our global presence. And to that end, You can see our global footprint here. So we have 17 global manufacturing facilities, which makes us very nimble and able to supply globally our products globally. Those manufacturing facilities are across 4 continents, so Australia, Europe, Asia, and North America. We're over 1,700 employees, and a neat fact is we do over 1 billion liters of fluid annually. So 1 billion liters of fluid goes through our global plants and to our end customers on an annual basis. So we rely on, our superior R&D, our strategic manufacturing, and our broad product portfolio to really, drive market share and offer our expertise into the industry. Okay, so this is the last of the corporate slides, but my favorite of them because it focuses on the research and development aspect. And this will also serve as a nice transition into the case study where we'll look at the development of a new automotive fluid specifically for thermal management of electric vehicles. So the PFX research and development department is really broken into 3 core functional items. So we have product development, product support, and then industry engagement. On the product development side, so we have 3 main R&D facilities in North America. 2 of them are located in the United States, 1 is in Canada, and we develop our products from scratch, right? We formulate our products. We have expert scientists in-house across chemistry, analytical, thermal engineering, mechanical engineering. So we build the formulations from the ground up. We run all of our own testing, all the way from bench tests through in-vehicle fleet tests. We also maintain OEM relationships. And then to the point of the in-house formulations, this is backed up by our robust intellectual property portfolio that supports all of these products that we take to the market. Product support, so we don't just sell the product and then walk away. We want to be involved with the customer in the end use. We answer questions. We have labs set up that can do analysis of in-service coolants. We do material compatibility testing, things like rubbers and elastomers if a customer has a concern about a new type of material that's in their system that might come in contact with the coolant. And then finally, we do technical training sessions for customers, liquid cooling engineers, not so dissimilar to what we're doing today, right? An educational overview of what these fluids are, how they're developed, and how they can be used. And then finally, we are very active in the industry. So there's a couple examples up here. So ASHRAE is an organization focused primarily on stationary heat transfer fluids. ASTM covers a wide range of specifications. Our group is very active in the ASTM D15, which is the coolants group. We actually chair 5 different committees within that group, including the low conductivity electric vehicle coolants, and then open compute. So this is another one. This is a newer area. And it relates to liquid cooling of data centers and AI factories for high performance compute. So we are active in these specification writing groups, and we'll talk a little bit more about some of these specifications specific to the electric vehicle thermal management fluids that are coming out of some of these organizations very shortly. All right, so for the bulk of the content for today, here's an outline of the story that I want to tell. So first, we'll talk about thermal management fluids for an electrified future. What is electrification and why does it demand thermal management? We'll focus specifically on the electric vehicles. So electric vehicle functional fluids, what fluids are in an electric vehicle and which ones pose a potential safety concern. And then development strategies. We've identified a need in the market for a new fluid. How do we go about developing a fluid as Prestone? And then once that formulation is developed, how do we test it and validate it, make sure that it holds up to what it needs to do to meet these new specifications? And then finally, and above and beyond, step 6, how do we ensure that our fluid is safe, right? So we meet a specification, but we want to see our own data that shows our fluids are safer than incumbent technology. So this is what we're going to walk through, and I hope you will enjoy the process, and I look forward to addressing any questions around our development process at the end of the presentation. So thermal management for an electrified future. So what does this mean? So in the introduction, right, I was introduced as the director of our electrification team at PFX. So how have we grouped everything in electrification together, and why does this make sense for us? So the electrification team really takes ownership of 3 unique areas in the market. That's electric vehicles, what we're talking about today. That's data centers, which are using high performance compute and increasing amounts of energy. And then that's battery energy storage systems. And this really supplements both of these fields by being able to store electricity so you can use it on demand when it's needed. So thermal management plays a critical role in all of these different areas. In electric vehicles, for instance, the rate of charging is directly related to how quickly you can cool the batteries or how efficiently you can remove heat from the batteries during the charging process. Similarly, efficient thermal management relates to the range of your electric vehicle. How far can it drive on a single charge? And finally, thermal management is critical for safety. Battery thermal runaway and thermal runaway propagation is one of the main failure mechanisms for electric vehicles that can lead to fires, explosions, and potential injuries to individuals near these vehicles. So efficient thermal management is critical for all of these areas. I won't go through all the other details in data centers and battery energy storage systems, but they're going to have similar demands and similar needs for thermal management fluids. With that, global energy demand, specifically for electricity use, are increasing at an extremely rapid pace. So it's anticipated that demand is going to increase 25%, electricity demand, between the years 2023 and 2030. The main drivers for this increase in electrification or in electricity use are really the new AI factories, so the data centers that are coming up from your hyperscalers. Every time you use a ChatGPT search, this uses an intense amount of electricity to power those graphics processing units that are doing the calculations to get you your answer. So that is a huge driver for increased electrification. And we can see in this table on the right here, just a mere 5 or 6 years ago on the data center side, an IT rack might have consumed 5 to 10 kilowatts per rack. We're already today, in the last 3 years, we've moved to over 100 kilowatts per rack. The latest set of chips from NVIDIA, which are by a large amount, the market share dominating GPUs on the market, those new line of chips require liquid cooling, right? It's not just recommended. The chips cannot be operated without liquid cooling. So we've gone from air cooling, being able to handle the thermal loads for everything in the industry, to now we have to use liquid cooling. And within the next 2 to 3 years, the goal is to move from 112 kilowatts all the way up to a megawatt of power per rack. Every time we increase electricity, we're going to increase the thermal waste that comes with it. That is a fundamental principle of physics. Anytime you have electrons traveling through a conductor, you have current flow, you're going to have resistance, which will lead to resistive heating. So the more current you have, the more heat you have. So as these things go to higher powers, you're going to need a more efficient thermal management mechanism. The story is the same on the electric vehicle side. We can look at chargers. Level 1 and level 2 chargers, they can use passive heating because there's not an extreme amount of current flowing through. But with these chargers, you're going to be waiting 6 to 12 or longer hours for your vehicle to be fully charged. As we move to level 3s and level 4 chargers, we start demanding liquid cooling again. So the majority of the level 3 chargers, which can charge your vehicle in closer to that, getting to less than an hour range, these are going to be liquid cooled to make sure that you can dissipate that heat and not have your components being damaged from an excessive amount of heat running through them. So this trend is happening now, and it's going to continue happening. And so this is, these are the reasons why we need to develop these robust thermal management solutions for these electrified end uses. The other thing to keep in mind, besides just efficiency of heat removal, is we're talking about high voltage components. Now, if you think about salt water and electricity, they don't really get along, right? When there's a lightning storm outside, we say, get out of the pool, get away from water. And that's because the fluids can be conductive. And when high voltage hits those fluids, they can transfer electricity through them, which can lead to shorts, electrocution, generation of explosive hydrogen gas, and in a worst case scenario, spontaneous thermal runaway of your battery cell, which leads to a fire or some sort of catastrophic event. So that is the commonality between all these things, moving to higher power requirements while continuing to use high voltage with liquids nearby. And so in terms of the electric vehicle market, so focusing back on here, we can take a look at the global market for electric vehicles. And as and so, no surprise to us, China is the dominant market share leader in electrification of the automotive sector, accounting for nearly 64% of new vehicle sales for electric vehicles in 2024. They're followed by the EU at around 18%, and then North America around 10%, with the rest of the world coming in at 8% behind that. And then globally, if we look at the car park in terms of new vehicle sales in 2024, as I mentioned a few slides ago, 80% of the new vehicle sales are still internal combustion engines, but hybrids and pure electric vehicles are starting to take significant market share to the point where their combined market share is now 20%. And then breaking this down just regionally in North America, we see the dominant shareholder for electric vehicles is still Tesla, around 50% market share, followed by GM, Hyundai, Kia, Ford, BMW, and the rest of the OEMs make up the remaining portion of the electric vehicles in North America. And so Prestone, right, we already have a presence in electric vehicles today. So some of our most iconic fluids are filling thousands of vehicles, thousands of electric vehicles that have been in operation for years. So that just goes to show the universal nature and how the widespread application of our current fluids. That said, new for 2025, we are launching the Prestone EVX. What's special about Prestone EVX? This is a specifically formulated fluid for electric vehicles. And the key to it is it maintains a low electrical conductivity, so we can mitigate any of those potentially devastating interactions of a fluid with a high voltage electrical device. So this fluid is developed for vehicles that are requiring low conductivity fluids, like all of these vehicles that will be going into China after October 1st of this year. All right, so safety considerations. We've started to touch on this, but what are the true safety considerations of the fluids within an electric vehicle? It's often a misconception that electric vehicles don't have any fluid because they have less moving parts than an internal combustion engine. That's not fully true. There might be less fluids, right? There's no need for an engine oil, and there's no need for certain gear oils within your electric vehicle. But that said, there are still a number of other fluids. So we have an e-axle fluid that lubricates gears and moving parts between the motor and the wheels. And that's going to be around 12.5 liters of fluid. You've got refrigerant, you've got brake fluid, you've got your traditional battery thermal management fluid or antifreeze coolant. And then notably here, this is the highest volume fluid in the electric vehicle at about 14.5 liters. And then finally, you've got a washer fluid. So the other thing I want to call out about these fluids is the highest electrical conductivity fluid, which we've already identified as a potential safety hazard near high voltage vehicles, is not only has the thermal management fluid has the highest electrical conductivity, and it's also the closest fluid to the battery pack, which is most prone to thermal runaway and fires. So we identify this as a potential issue, and not just us, but these standard organizations like GB. So we've identified our target to improve the electrical conductivity of the traditional battery electric vehicle. But as you'll see as we go through this exercise, it's more than just reducing electrical conductivity. It's also ensuring the performance of the fluid on the corrosion side and the heat transfer side. So thus begins our challenge. But just to give you a little bit of real world examples and confirmation that this is an issue in the real world application, we have seen numerous instances where high electrical conductivity thermal management fluids have led to battery thermal runaway and fires with lithium-ion battery packs. And this can be both across automotive as well as stationary. So there's examples of battery energy storage systems that have had coolant-initiated thermal runaway events. And then, for example, here you'll see a picture of Class 8 pickup trucks. These were battery electric pickup trucks. 2 years ago, there was an engineering oversight that led to leaking coolant into the battery pack, and numerous of these trucks caught fire while sitting parked in a parking lot due to this engineering deficit in the design. So there are numerous standards out there to address electric vehicles and battery safeties today. It's not like this is just coming out of nowhere. Groups like UL and ISO have been developing standards since electric vehicles started hitting the roads. But most of these standards relate to full vehicle safety or battery pack safety, and mostly hard goods and mechanical safety. So we're just now, as we're ramping up the presence of electric vehicles on the road, starting to uncover some of these new issues like the potential risks of high conductivity coolants. So again, this goes to state that GB out of China is leading the market in terms of low conductivity or implementing the necessity for low conductivity coolants. And this was one of the driving forces for the development of our Prestone EVX product. ASTM and SAE are not far behind, developing similar standards that will be specific to electric vehicle coolants. And we can talk about that a little bit more, right? So these upcoming specifications that are specific for the thermal management fluid within the electric vehicle. So GB 29743.2. And again, this is the standard specification committee out of China, who represents the transportation department. This specification in particular calls out 100 microsiemens as the maximum electrical conductivity for the fluid. So you'll remember from about 2 slides ago, we saw that a conventional or a traditional internal combustion engine has an electrical conductivity between 2,500 and 5,000 microsiemens per centimeter. So we're looking at orders of magnitude decrease in electrical conductivity. Now, in addition to that, there's still strict corrosion protection requirements. And as you'll see when we go through our development timeline, that these things are kind of at odds. We're going to be balancing electrical conductivity with corrosion protection. And then finally, just to reiterate, this is happening now. So we're less than 2 weeks away from the implementation of this standard within the nation of China. ASTM is another organization very active in automotive coolants. So ASTM D15 and ASTM D15.26 specifically is the subgroup focused on electric vehicle specific thermal management fluids. There is an existing standard out of ASTM for glycol-based electric vehicle coolants. This is ASTM D8566. Admittedly, this is a softer standard compared to the GB standard. It still requires less than 100 microsiemens of electrical conductivity, but the corrosion testing requirements are not up to the same level of scrutiny as the GB test. And then finally, this group is a little bit newer, but in terms of the Society of Automotive Engineers, or SAE, they just recently formed a low conductivity thermal management task force for electric vehicle fluids. And I serve as the chair for this committee, and I'm happy to say that about a week and a half ago, we officially received our J document, so J3359, which is still in draft form. But this will define the requirements for electric vehicle low conductivity thermal management fluids through the SAE organization. So more standards are coming. And again, this is the motivation for developing these low conductivity products. And so Prestone's been working on this for a number of years. And we've developed 2 products to meet these specifications to fit different market needs. So the first product is a low conductivity phosphated oat type coolant. This is less than 100 microsiemens. It comes in around 88. It meets all of the requirements for GB 29743.2, that Chinese specification. It utilizes proprietary organic phosphate inhibitor technology. So this formulation, as I mentioned before, is unique, built from the ground up out of our R&D facility, a very unique technology. Notably, we were able to produce this fluid without the use of silicate, borate, nitrate, nitrite, or amine, which not many other fluids have been able to do thus far. And then also notable, this fluid has exceptional stability against flux-brazed aluminum components. And I'll show a little bit of that data in a few slides. The second option is the HOTE type product. Now, this is a silicated product, still meets the GB 29743.2 specification. Low electrical conductivity, 75 microsiemens. And the benefit here is this has a higher RA due to an organic RA boosting additive within the formulation. So 2 different flavors of GB compliant formulations are ready out of Prestone EVX. So how did we develop these products, right? I showed you what they do, what the claims are, but I want to walk you through how our group goes about developing a new product when we have a justification and a motivation to do so. So the first thing we do is we break it down into 3 sections, right? Any good battery thermal management fluid, or any heat transfer fluid in general for that matter, is going to have 3 key properties. There's going to be your thermal properties, which really dictates how well the fluid transfers heat. And this is primarily driven by 4 different physical properties, and those are viscosity, thermal conductivity, specific heat capacity, and density. The second category is safety and environmental. The fluid has to meet local, regional, national regulations. All of the ingredients in it must be listed on chemical inventories in the regions where you want to do sales. But beyond that, we think about other things like global warming potentials, life cycle analysis, the inclusion or exclusion of PFAS, right? So we want to make sure that we don't have any forever chemicals in our formulations. And then finally, material compatibility and durability. So this is critically important and shouldn't be overlooked. This is the first stage of safety in any heat transfer fluid, but specifically for electric vehicle fluids. If you don't have good corrosion protection or material compatibility, your fluid can degrade the components which are meant to contain it, and this can lead to leaks, right? You can have buildup of corrosion deposits, which can lead to blocks, or you can have corrosion through a material, which leads to a leak, which in a worst case scenario could leak into a battery pack and cause a fire. So these are the three things we care about when we're starting at the drawing board to put together a new formulation. Now, electric vehicle thermal management, there's really two different trains of thoughts on how to approach it. So one is indirect thermal management. And in this case, the battery cells or the battery packs sit on top of a heat sink called a cold plate that has microchannels inside of it, where you have a cold fluid flowing in one side of this. They pass through the channels. They extract the heat that's transferred from the battery cell into the heat sink, the cold plate, and then they come out the other side, the hot stream. And then they go to a heat exchanger where that heat can be exchanged into the environment or with another component that requires heat to operate optimally. The second strategy is direct immersion thermal management. In this case, we remove the indirect heat sink. The battery pack is submerged directly in the fluid. So think of a bathtub and the battery cells just getting put directly into it. So these types of fluids require a whole nother level of electrical insulating properties. So when we talk about less than 100 microsiemens fluids, that is not sufficient to be a direct immersion fluid. These are typically oil-based fluids that do not carry current at all, practically. So you have to have a very, very insulating fluid. The benefit of the immersion cooling strategy is you get complete surface area coverage of that battery cell, which is generating heat, so you can remove heat more efficiently. Now, this technology is talked about often, it's researched extensively, but today we're still seeing essentially all vehicles on the road, both passenger car and heavy duty, using the indirect thermal management technology. That's not to say that immersion isn't going to happen. We think there is a good opportunity for it, especially in certain end uses. But today, the primary means of battery cooling is through indirect thermal management. And so, we can see that the current gen technology for battery cooling, power electronics, the one place where we can deviate from that is motor cooling. Motor cooling has moved to the position where it's nearly 50% indirect cooled with water glycol and nearly 50% direct cooled with an oil-based fluid. Generally, it's your e-axle fluid that's used within the system. Fuel cells are another topic that we're not going to dive into today, but I just want to mention that fuel cells require another additional decrease in electrical conductivity compared to battery electric vehicles. And this is because the fluid in the fuel cell is routed directly through current carrying bipolar plates. So if your conductivity is too high for this fluid, you can have transfer of energy through the fluid, which leads to decreased efficiency and shunts between your cells. So that's all we're going to say on fuel cell cooling today. We're going to spend the rest of the time focused specifically on indirect thermal management fluids for battery cooling and battery electric vehicles. So general properties of a traditional internal combustion engine coolant versus a low conductivity battery electric vehicle fluid. At face value, these two fluids look very similar. They're both going to use ethylene glycol at between 40 and 60% most commonly. Where we start to see a little bit of deviation is electrical conductivity. So we touched on this. Traditional coolant, 2,500 to 6,000 microsiemens per centimeter. Low conductivity coolant is going to be in the range of 5 to 100. pH range, again, maybe a little bit tighter for low conductivity BEV. And this is generally due to the lack of ability to put ionic bases into the formulation that would get you to those higher pHs. due to the conductivity contribution that would come with those additives. Another place where we see a little bit of deviation is in the corrosion inhibitors or additives that are used. So the primary contribution to electrical conductivity in a coolant or a heat transfer fluid comes from the additives or the corrosion inhibitors that are in there. So traditional ice coolants use things like organic acids, phosphate, silicate, borate, nitrate. These compounds, these additives are all ionic. And as we already mentioned, ionic compounds carry charge and they transfer electricity. So the biggest challenge to us is to be able to formulate with either a new set of additives or a unique combination of some of these ionic additives that maintains their corrosion protection while minimizing their contribution to electrical conductivity. So we see a lot of things like azoles, some silicate, phosphate or organophosphate, and commonly we see the inclusion of amine, which allows you to get that increased basicity, increased RA, without having to use something like hydroxide, which is going to be a big contributor to electrical conductivity. And then finally, the last consideration is around compatible metals. Your traditional ice coolants are looking at, a wide range of, you've got copper, brass, solder, stainless steel, cast iron, and aluminum. The battery electric vehicle type fluids are generally more focused on aluminum heavy systems. So there's lots of different grades of aluminums, and this is in addition to copper, brass, and stainless steel. So the GB specification requires compatibility with 4 different grades of aluminums in addition to those other metals. All right, so those are the things we're thinking about. So we've got an idea, we've put together our preliminary formulation. How do we test it? How do we validate it? How do we know that it's going to hold up once it actually makes it to a vehicle? Coming back to this concept of low conductivity and compatibility, these are the 2 things that we're looking to balance. So corrosion protection is key. We need to be compatible with metals, but not just metals and corrosion, but the elastomers, the rubbers, the wires, the connectors, the coatings that are in the thermal system. So this is step 1, doing material compatibility testing, in addition to the corrosion testing, right? So this is the initial performance evaluations that tell us whether or not we have a viable coolant to move forward with testing. Again, to reiterate, the primary contributor to electrical conductivity in an internal combustion engine coolant are the ionic corrosion inhibitors that are added. So we don't want to reduce conductivity at the expense of corrosion, because this can lead to rust, buildups, leaks, blockages that can be detrimental to the cooling system. So here's what this process looks like from start to finish. The first thing we do is we measure all of the physical properties of the coolant and make sure they're in line with whatever specification that we're looking to meet are. So these can be things like freeze point, percent of glycol, pHs, reserve alkalinities, all of these different physical features that tell us a lot about how the fluid might perform from a thermal perspective within the fluid. Next, we move on to bench corrosion evaluation. So there's a number of tests which we use to evaluate how well the fluid is going to protect the system against corrosion for the metals that come in contact with the fluid. We then move to a simulated service test. This test takes specific components from the electric vehicle cooling system, puts them all into one unit, and we run, this test is meant to mimic the conditions that we see within an electric vehicle thermal system. We then finish out the durability testing, looking at things like flux compatibility and hoses and things of that nature. And then finally, we finish off the test once we're confident in the formulation with a fleet test. And this is something, that at Prestone we're very proud of. We run many, many fleet tests and many, many miles out of our research and development department every year that leads to good real world data that can support our laboratory test data and claims. So we're going to walk through each one of these different categories. Assuming we're past physical properties, so that most of that is done by our analytical department. And once we meet all the physical properties for the specification, we move on to the glassware corrosion test methods. Now, what I've done here is summarize some of the differences. So these types of glassware corrosion test methods are very similar, whether we're looking at an internal combustion engine fluid or an electric vehicle fluid. What differs are some of the conditions. In each case, we're going to take a bundle of metal specimen that includes those metals from the cooling system that we're interested in. What we're looking at here is an ASTM D1384 bundle with copper, solder, brass, steel, cast iron, and cast aluminum. These bundles are then placed into a vessel that contains coolant. They're heated to a specific temperature. They may or may not include corrosive salts to accelerate the rate of corrosion. And then they're held for 2 weeks. And then at the end of the test, we tear it down. We clean this metal specimen. They go through a water wash and then an acid wash, and we take a weight of them. And we can measure a weight loss from before and after the test. And that tells us what our rate of corrosion is for that specific metal in this bundle with a specific coolant. And so you'll see some of the differences from the ICE test to the EV tests. As I mentioned, the GB EV test is more severe than the EV ASTM test as it currently stands. And some of the differences that will make things more or less severe, things like galvanic coupling. If you put a metal coupler between two of your metal specimen, this is going to increase the severity of the corrosion test. Corrosive salts is another one that I mentioned. Test temperature. So while this test is generally run at 88 degrees Celsius, we've reduced the temperature, or the committees have reduced the temperature to 80 degrees Celsius for the EV tests, as we don't reach the same max temperatures that we see in internal combustion engines. But we've left the time the same. These are 2 weeks for all of these tests. And then so at the end of the test, right, we work up the data, and what does it look like? So this slide is designed to calibrate your minds for what it is that we're looking to do and what the scope of results can be. So we've put on the far left, if we start in the top left quadrant here, we've run a baseline or negative control that is just ethylene glycol and water with no additives in it. And you can see we have an extreme amount of weight loss for the steel coupon here, of over 250, almost 300 milligrams of weight loss for this sample. So this is a clear fail. Just to level set, there's a line here at around 10 ppm. That is the threshold for a pass-fail in this corrosion test. That is weight of the metal that's lost from the coupon at the end of test compared to the fresh metal specimen. If we put a traditional high conductivity internal combustion engine coolant through this GB specific glassware corrosion test, it passes the test no problem, right? And this isn't a surprise. We know that the Prestone coolant is very robust, but it won't meet the spec because the conductivity is over 100 microsiemens. So then we look at a poorly formulated low electrical conductivity fluid, and this is number 3 here. And we can see just from the visual of the poorly formulated low conductivity end of test specimen that these specimen have been terribly eaten away and corroded by the fluid in there. And so this fluid is actually a fluid that was commercialized as a low conductivity EV fluid prior to the GB specification being released. This fluid was later recalled due to corrosion issues within the system. Now, what does a good fluid look like at low conductivity? You'll see the results are much, much closer to that traditional ICE coolant. This is our Prestone EV low conductivity POT, sample number 4, and you'll see that it passes with less than 10 milligrams of weight loss for all of the metal specimen, and we have a very clean looking specimen. So we've now been able to show corrosion protection while maintaining less than 100 microsiemen electrical conductivity. So this is step 1. We finish this out with some additional corrosion testing. We have a high temperature aluminum heat rejection test. If you're familiar with ASTM test methods, this is a modified version of the D4340, with the modifications being to the type of aluminum used. And then we move on to the simulated service test. So you'll see the results for our corrosion are very acceptable per the GB specification. And then we run the simulated service test. So this is a similar test, except in this case, instead of it being stagnated, we have a flowed fluid and we have additional components, including heat exchangers, motor housings, and cold plates, which will much better represent the actual conditions within an electric vehicle thermal system. And again, you can see weight loss levels for all of the metals in the bundles that are used in the simulated service test fall well within the scope of the limits for the test, again, implying excellent resistance to corrosion. Flux brazed aluminum. So one of the biggest developments in automotive in recent years is transitioning from arc welding to flux brazing. And this has reduced costs and increased the rate of part production for a lot of these parts manufacturers. But that introduces a new challenge to coolant suppliers like us, because this leaves behind a flux residue. They use a paste called flux. It's heavy in aluminum and fluoride, and it bonds these two aluminum metals together. And so this can be an issue. In the past, certain coolants have struggled to have compatibility. It can lead to deposits and clogging and overheating of components and potentially leaks. So what we do is we run a accelerated test. We call it a radiator cube stagnation test. We cut up the radiator from a light-duty vehicle into cubes. We weigh these cubes, submerge them in the fluid. These are cooked at 90 degrees Celsius for 4 weeks, and we take the coolant out. We analyze the coolants, and we visually analyze these samples. And so the first thing I'll call out, so these are 3 different samples of radiator cubes. These are the end of test pictures on the bottom right. You'll see the samples on the far left are the Prestone EVX fluid. They're shiny and clean. The other 2 samples, which are GB passing fluids, they have some buildup, some deposits, what looks like a little bit of maybe oxidation product on the surface of the aluminum radiator. And we can see that in our data, right? So the one thing to note, electrical conductivity, end of test increase for the Prestone fluid, we're still under 100 microsiemens. For the competitive fluids, they start at 77 and 94 microsiemens respectively, and their end of test value is over 300. So significant increase for those fluids. Fluoride levels is another important one to call out. You'll see that the Prestone fluid picks up around 10 ppm of fluoride, and I've just covered it up there. So the other 2 fluids pick up 120 and 160 ppm. And then finally, aluminum. That's another critical component for the corrosion aspects. No aluminum detected in our end of test fluid, where we have 30 and almost 60 ppm for the competitive fluids, respectively. And then one other thing to look at here is retention of azole inhibitors. So azoles are critical for yellow metal protection, your coppers and brasses. The end of test from this radiator cube stagnation test, we retain 100% of our azoles, where the competitive fluids for our POT fluid, almost 80% for our HOT fluid, versus competition where we see significant over 50% depletion for both of those fluids. So again, very robust fluids, particularly the phosphated OAT type fluid when we talk about resistance to flux brazed compatibility interactions. After that, right, we've got data, we're confident in the fluid through all of the bench tests. What do we do next? We put it in a vehicle or multiple vehicles, and we run a fleet test. So this is an ongoing fleet test right now. We're running these Ford Mustang Mach-E's out of our R&D facility here in Danbury, Connecticut. This is a very controlled test. So I'm not going to show data because this is still an ongoing test. But what we see here is that, you know, our process for setting up these tests is very controlled. Our data is very repeatable and reliable. We have a sampling schedule that is make sure to capture all of the minute changes from everything from electrical conductivity to percentage of glycol, your inhibitor levels, your glycol degradation products. And we monitor all of these things. We plot them throughout the entirety of the test. So again, this is another thing that, you know, not all coolant manufacturers do, that Prestone is very proud of and leads to the superior products that, you know, we put onto the market. Okay, so we've gone through our entire development cycle here, right? Physical properties, corrosion evaluation, simulated service, durability, and fleet testing. So this is what's required to meet these specifications. But at this point, you know, we're still not content. You tell us that our fluid is safe because it's less than 100 microsiemens, but we want to see this for ourselves, right? We want to see how does our fluid interact within the field of an electrical current. So before we get towards this, let's look at battery pack architecture. So there's a lot of different ways to do this. You're going to have different form factors of cells. You've got some new designs like, you know, cell to pack. But traditionally, this is how battery packs are put together. You're going to have cells at the smallest level, and these are going to be 4.2 volts, maybe 2 to 50 amp hours. These are combined both in series and parallel to put together a module. You've now linked these battery cells together, and you might have a voltage around 42 volts and maybe, you know, 5.3 kilowatt hours for your module. And then these are further connected together to give a battery pack. Battery packs can be anywhere from 400 to 1,000 or even higher now volts. and their capacities can range from 50 to over 150 kilowatt hours. So 150 kilowatt hours is a significant amount of energy. If you've never seen all of that energy released from a battery pack at once, that's probably for the best, because that would be a very explosive type of event. So unfortunately, it's not practical for us to test our fluid with a full battery pack. However, we can mimic these different voltages at the cell, module, or pack level by using a power supply. So this is what we do. We take two copper electrodes that would represent both the bus bars within an electric vehicle that carry current from the battery pack to the devices they power, as well as the tabs on the battery cell. We supply power through a high voltage power supply, and this allows us to use to match the voltages of a battery electric vehicle module or pack without the stored energy that could be instantaneously released to lead to a catastrophic failure. And then what we can measure is a number of critical parameters, right? So we'll look at our peak current, how much current passes between the electrodes, the temperature, as I mentioned earlier. Anytime you have current passing through a conductive medium, you're going to have joule heating or resistive heating. That's this red line. And then we look at the profile of the current over time. So current depletion, do we have passivation? Does it increase? There's a lot of different trends for different fluids. This is just one specific example. And this electrolysis testing was done at 42 volts. So this mimics a module level battery configuration. And we run these tests in-house. So 42 volts, we're happily able to safely handle in-house. And here's what that looks like for a range of different coolants in descending electrical conductivities. So there are some trends here that might not be universally true, but generally the higher electrical conductivity fluids lead to a higher amount of deposits on the electrodes at the end of test. Specifically, as we move to the low conductivity, right, you can see our fuel cell coolant at 5 microsiemens, essentially no reaction with the current. There's no buildup. And then as we move to the left with some of these higher electrical conductivities, we have a significant amount of deposits. This is 42 volt testing. This was nice, but we really wanted to move this to pack level voltages. And so we wanted to look at comparing our new low conductivity fluid with one of the incumbent fluids that's used as factory fill in one of the most popular electric vehicles today. And that's this G48 product shown down here on the right. So we outsourced this testing, and we're doing 400 volt and 800 volt electrolysis and then live battery cell testing. For today, I have the 400 volt data ready to share with you. If you're interested in the 800 volt or the live battery cell data, come see us at the battery show in Detroit in October, because we will have that data ready to be presented at that time. So keep that in mind. So we're looking at the same types of things here. We're looking at the temperature profile, and then we're looking at the current for the fluid as well. And so I'm going to show you a video, and then I'll walk through what some of this current actually means. Hopefully this is going to play here. So this is the low conductivity Prestone EVX fluid at a speed of 1 times to start. You're going to see when the electrolysis starts, there's a little bit of bubbling happening at the electrode. It's not aggressive, it's fairly mild. This is expected as we have a small amount of current passing. We're going to have a little bit of fluid electrolysis. So it's so mild that I was able to speed this up to 15 times, get through the entire 10-minute test video. A little bit of deposit buildup. Really nothing too aggressive, nothing too aggravating. I'll also note there's a hydrogen sensor set up in the test cell. As you pass current through the fluid, it will electrolyze the water and the glycol in the fluid and will generate hydrogen gas and oxygen gas, which as they combine can become explosive. So if we want to look at the data for what we just watched, right, we saw bubbling between 2 electrodes. What does that really mean? So this dark blue line on the graph here shows the temperature profile. So we start around 25 degrees Celsius, and this increases to 70 degrees Celsius at the end of 10 minutes. So this test lasted 10 minutes. We did see an increase in temperature, but we're still well within the safe range for battery thermal runaway. And then notably, our current, we started around 300 milliamps and finished just shy of 500 milliamps. So as a fluid heats up, The electrical conductivity is directly related to the temperature of the fluid, and so this is unsurprising. This matches what we would expect for the higher temperature electrical conductivity for this fluid. Now, let's look at the high conductivity G48 type fluid. So this is a 4,000 microsiemens fluid, and this will be the next video that we're going to watch at 400 volts. And you'll see immediately we see a much more violent reaction. And then if we keep an eye on this, about 8 seconds in, the hydrogen alarms go off because they've tripped for detecting their lower explosion limit within that laboratory. So they immediately, within 12 seconds, hit unsafe conditions for the laboratory, and there was a concern of a hydrogen-initiated fire. Now, that's the 400 volt data. So to walk through that on the graph here, I got to go back. Apologies. We look at the peak current. Sorry about that. I think I have to let it play now. All right, give 1 second. Oh, I was able to skip it. Okay, here we go. So I'll let this play through. Okay, so since I can't get it up and running, we're just going to go to the last slide. But in general, right, that test ended within 12 seconds. We had an extremely high. We maxed out the current rating on the power supply, and as you can see, there was an extreme amount of hydrogen gas coming off that led to a safety concern. So wrapping this up, electric vehicle fluid safety. We just walked through the development process for a new low conductivity EV-specific thermal management fluid from Prestone. We've showed that it's low electrical conductivity and compatible with high voltage components. It resists corrosion, and it's compatible with modern aluminums from assembly processes. And finally, we took it all the way to safety testing and have looked at the interactions of our fluid in high voltage systems that would mirror that we see in electric vehicle technology today. So with that, I will end my portion of the webinar and happy to pass it over for any questions on the content.
Terrific. Thank you, Tom. And before we get to our Q&A, I'd like to ask all of you to direct your attention to our survey available next to the presentation window. And if you close the survey, you can reopen the widget by clicking the icon along the bottom of your screen. Again, thanks. Your participation just makes these events better for you. And now on to our Q&A. As a reminder, to participate, just type your question into the text box located next to the presentation window or click the Q&A icon at the bottom of your screen. I don't think we will have time for all your questions today, so I'll share them with Tom, who can get back to you offline. So let's start with a question from Leslie, who asks, do we know when the standards that China is adopting will become more widespread globally?
So what we're hearing from a lot of the OEMs who are kind of the decision makers, given a lack of legislative forcing, I guess, to abide by these standards, is they're going to look and see how China fares with these new low conductivity fluids. It's a bit of an unknown still, right? I would say with Prestone having a fleet test, we probably have as much or more data than just about anybody else.
Right.
I would look at the next few years, though, as these specifications roll out. So they'll roll out as guidelines, and then it will be up to the regulatory agencies to implement them as laws.
Terrific. Keep the questions coming. This one from Luca, who wants to know, how do you anticipate the future adoption of EVs to be globally?
I don't think that the adoption of global EVs is going to slow down anytime soon. If anything, we see most regions accelerating year-over-year electric vehicle sales. Obviously, China is driving this. They're well over 50% of new vehicle sales being electrified. Geopolitics will play into that, but I think that we have enough of momentum behind electric vehicles at this point, given the technology advances that are reducing costs and alleviating some of the anxieties people have around range and charging time. So as those things continue to advance, we'll see more and more implementation of the EVs.
Terrific. This one from Leslie, who wants to know, do all of Prestone's thermal management fluids for EVs, both the new EVX and the existing fluids that OEMs are using, Are they formulated to meet the China GB spec or only the new PFX?
Yeah, only the new Prestone EVX fluid will fully meet the specification, and that's because that legacy yellow jug fluid is too high of an electrical conductivity. While it's used in electric vehicles today, and it works very well. We haven't had issues. The electrical conductivity of it would result in it not meeting that specification.
Okay, thanks. Keep the questions coming. Again, I'll share the ones we don't have time for with Tom to answer offline. Cedric wants to know, is Prestone EVX good for data center cooling?
Interesting question. So we have a version of the Prestone EVX low conductivity for data center cooling. It's slightly different. The main difference between data center coolants and electric vehicle or automotive coolants is data center prefers propylene glycol for the lower toxicity profile. So generally they're running 25% propylene glycol rather than 50% ethylene glycol. But we do have a low conductivity formulation for data center.
Okay, thanks for that. This one from Matthew, who asks, what kind of warnings will be on the SDS for the EVX fluids? Most organophosphates are extremely toxic, like high-end pesticides and nerve agents. So what kind of precautions will be needed to safely handle this fluid?
Yeah, that's a good question, and it's an area that I have a lot of experience in. So I actually did my PhD on organophosphorus pesticides and nerve agents. So I can confidently say that any of the chemistry within our formulation does not pose any regulatory issues in terms of the safety concerns with some of those organophosphorus nerve agents. So this we're well away from those types of structures that would lead to any potential health concerns.
Great. Keep them coming in. We only have a couple of minutes. I'm going to squeeze in as many as we can. Angela wants to know, are the new low conductivity fluids backwards compatible in ice applications?
Today we would say no, because we haven't done testing in ice applications. We talked a little bit during the webinar around the different conditions, so the hotter temperatures. So we would generally not recommend a low conductivity for an internal combustion engine today. The data isn't there to support that.
Okay. Jim wants to know, how often do you recommend that BCF is changed? And is it based on miles or time?
So that's another good question that we're getting closer to knowing an answer on. It's likely going to depend on the rate of conductivity increase for the fluid. So there's talk about the GB specification, talking about 300 microsiemens being that cutoff point. We will probably try to tie a mileage to that rather than a time, but it's still to be determined. Lifetimes for the fluid will likely not be to the same claims you see on like the Prestone Yellow Jug, 350,000 miles, but we do expect them to be sufficient where you're not having to go change your fluid every 3 months.
Okay, great. Justin wants to know what you think for stationary energy storage systems cooling.
Yeah, stationary energy storage systems. So this would be a very good fluid for those systems. We do service the stationary energy storage market today with some of our other fluids. They're going to be very similar conditions. You do want that freeze protection because a lot of these are outdoors, so you're going to want to make sure that you have good low temp properties. But for example, there was a Tesla Megapack in Australia that actually had a coolant-initiated fire. So we do think that this low conductivity fluid would be an excellent replacement for those traditional higher conductivity fluids that are used today.
We have just time for one more question. This is from Michelle, who wants to know, are these low conductivity fluids more prone to gelification?
Our fluid is not, I will say. Some of them are, and that's what I was getting at with some of that flux compatibility testing. So certain, poorly stabilized inorganic additives will gel when they contact flux or, under certain conditions. Our fluids are very stable through all of our testing. So we have no gelling and no deposit formation when in contact with the flux-based component.
And that's all the time we have for questions. Thanks, Tom. We appreciate your expertise and your time on today's topic. And thanks to our sponsor, PFX, as well as to everyone in the audience. We appreciate your attention and participation in the Q&A. And again, the questions we didn't have time for, we will share with Tom to get back to you offline. Within the next 24 hours, you receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been able to attend the event live. On behalf of our guest, Tom Corrigan, I'm Michael Krieger. Thanks for your time, and have a great day.
Thanks, everyone.